So welcome to lecture 9. So under lecture 9, we are going to look at energetics and Haber cycle. So first of all, you're going to begin by looking at the first part of that topic, which is energetics. So remember, when we talk about energetics, we are generally going to deal with reactions which involves energy changes. So remember, all types of chemical reactions involve changes in energy, but the most common form is heat energy. So remember, during a chemical reaction, there is breaking of bonds and formation of new bonds. So the bonds between the atoms normally break so that the atoms exist independently, whereby they will thereafter rearrange themselves to form the products. So therefore, that heat energy is normally expressed in terms of enthalpy and is given the symbol delta H. So generally, during a breaking of the bonds, heat is normally absorbed or heat is normally supplied, while during formation of new bonds, heat is normally given out or heat is evolved or released to the surrounding. So the reaction in which heat energy is given out is usually described as exothermic reaction, where more energy is normally obtained during bond formation as compared to the amount of energy which is involved during breaking of the bonds. So this reaction will result to the increase in the temperature of the surrounding because of the accumulation of heat in the surrounding. So the reaction in which heat energy is taken in is usually described as endothermic reaction. So that means breaking of the bonds will require the input of energy or supply of energy, while the formation of new bonds will involve release of energy. So much of the heat is required for breaking of the bonds as compared to the amount of heat which is given out during formation of new bonds. So this reaction will result to a decrease in the temperature of the surrounding because much of the heat will be absorbed from the surrounding. So then we move forward and look at this schematic diagram, which is illustrating a endothermic and exothermic reaction. So the first part is showing endothermic reaction, where heat is being absorbed from the surrounding to break the bonds existing between the atoms so that they can exist as free atoms. So you can see they are existing as free atoms, but in the next demonstration, you can see energy is being given out as those atoms come together to form new bonds. So the second part illustrates exothermic reaction or bond formation, while the first reaction illustrates endothermic reactions or formation of new bonds. So energy changes which take place during a chemical reaction can be represented by use of energy level diagram or energy profile diagrams. So the first profile demonstrates exothermic reaction, whereby much of the heat is involved during formation of new bonds as compared to breaking of the bonds. So you'll find that there will be the reactants will have much more amount of energy compared to the products because much of the heat is released to the surrounding during formation of the products. Then the next diagram illustrates endothermic reaction, whereby the reactants have a less amount of energy compared to the products. So much of the heat is involved in the formation of new bonds as compared to the breaking of the bonds. So therefore, products will have much more energy compared to the reactants. So the value of delta H for exothermic reaction is normally negative because remember, the products have less amount of energy compared to the reactants. But for endothermic reaction, the products have more amount of energy compared to the reactants, so it's normally given a positive value. So delta H for exothermic reaction is negative, while delta H for endothermic reaction is normally positive. So now average bond energy. So the energy needed to break 1 mole of a bond is usually referred to as a bond energy. So for us to determine the bond energy, delta H or enthalpy change is equals to enthalpy change for bonds broken plus enthalpy change for bonds formed, or the amount of energy which is involved in breaking the bonds plus the amount of energy which is involved in bond formation. So that one will give us a enthalpy change or heat of the reaction. So remember, bond breaking is normally given a positive value, while bond formation is normally given a negative value. So we want now to look at example 1. That example 1 demonstrates the combustion of ethane. So we have 2 moles of ethane which burns in air to form 2 moles of water in form of a gas plus 4 moles of carbon dioxide. So we are going to use various bond energies to see how we can determine the enthalpy of reaction for combustion of ethane. So this table is showing a bond energies. To break 1 mole of carbon-hydrogen bond, you require 414 kilojoules of heat. To break 1 mole of carbon triple bond carbon, you require 839 kilojoules of heat. To break 1 mole of oxygen double bond, you require 498 kilojoules of heat. To break 1 mole of carbon oxygen double bond, you require 804 kilojoules of heat, and so forth. So now we're going to see the number of bonds that exist in this particular reaction. So now, first of all, we want to define what is enthalpy of combustion. Enthalpy of combustion is the enthalpy change when 1 mole of a substance is completely burnt in oxygen to form the products. Or as per this reaction, the enthalpy of combustion is the enthalpy change when 1 mole of a substance reacts in excess oxygen to produce water and carbon dioxide. So the chemical reaction should therefore be simplified such that only 1 mole of ethane reacts in excess oxygen. However, let us look at these calculations here. So in this case, we have 2 moles of ethane combining with 5 moles of oxygen gas to give us 2 moles of water and 4 moles of carbon dioxide. So if we show these bonds, you'll find that in that 2 moles of ethane, we have 4 moles of carbon-hydrogen bonds. Then we have 2 moles of carbon-carbon triple bonds. Then in 5 moles of oxygen gas, we have 5 moles of oxygen-oxygen double bond. So the reactant site usually illustrates bond breaking energy, which is given a positive value, because remember there is absorption of heat in order for the bonds to break. But on the product side, we have 2 moles of water and 4 moles of carbon dioxide. So now under 2 moles of water, we have 4 moles of oxygen single bond, then 8 moles of carbon oxygen double bonds. So this one illustrates bond formation, and generally it will be given a negative value. So for us to get an enthalpy change, we shall take bond breaking energy plus bond formation energy. So now, under bond breaking energy, we have 4 moles of carbon hydrogen single bond. So we take 4 times 414 from the table. Then plus, we have 2 moles of carbon triple bond. So we take 2 times 839. Then plus, we have 5 oxygen, oxygen double bond. So we take 5. There are 5 bonds, then times. So 1 mole requires 498 kilojoules of heat. So this one is for the reactant side. Then plus, minus, a negative sign is for the products. So in brackets we have 4 moles of 4 moles of oxygen hydrogen single bond. So we take 4 times 4, 63. Then plus 8 times 8 or 4. 8 or 4 stands for amount of energy required to break 1 mole of carbon oxygen double bond. So when you work out, we shall get so bond breaking energy we shall get 5,824. Then plus minus for bond formation we shall get 8,284 kilojoules of heat. But remember, it is given a negative value because it is an exothermic. It is an exothermic process. So heat is given out. So when you get the sum of the two, we shall get negative 2,460 kilojoules of heat. But remember, we are breaking 2 moles of ethane. So to get amount of heat required to break burn 1 mole of ethane, you divide this amount of heat by 2. So we take negative 2,460 divided by 2, which will give us negative 1,230 kilojoules of heat. So the enthalpy of combustion of 1 mole of ethane is negative 1,230 kilojoules per mole. So you can have a look at that. So now we want to proceed and look at example 2. So example 2, you are supposed to calculate enthalpy of reaction for the Haber process. So under Haber process, we are forming a ammonia gas where we combine nitrogen gas and hydrogen gas. So 1 mole of nitrogen gas will combine with 3 moles of hydrogen gas to form 2 moles of ammonia. So when we show the bonds in the reactants and products we have, under nitrogen gas we have 1 nitrogen a triple bond. Then under 3 moles of hydrogen gas we have 3 moles of hydrogen single bonds. Then under ammonia gas we have 6 nitrogen hydrogen bonds. So now this table is showing now the calculations. So now under a bond breaking energy, under the reactants we have 1 mole of nitrogen triple bond, which requires 945 kilojoules of heat. Since it is 1 bond, we just take 1 times 945 to give us 945 kilojoules of heat. Then we have 3 moles of hydrogen single bond, so we take 3 times amount of heat required to break 1 mole of hydrogen bond, which is 436. So we take 3 times 436 to give us 1,308 kilojoules of heat. So when you get the sum of the two, we shall get 2,253 kilojoules of heat from that table. Then on the product side, we have 6 nitrogen hydrogen single bonds. So we take 6 times amount of heat required to break 1 mole of nitrogen hydrogen bonds, which is 391 kilojoules of heat. So we take 6 times 391 kilojoules of heat, which will give us negative 2,346. So remember, I'm putting a negative sign because this one is exothermic process, but bond breaking is endothermic process, so we give it a positive value. So now we proceed and get delta H, which involves enthalpy change for bonds broken plus enthalpy change for bonds formed. So it will be positive 2,253 kilojoules of heat plus negative 2,346 kilojoules of heat, which will give us negative 93 kilojoules of heat. But remember, from the previous example, from that previous example, we are forming 2 moles of ammonia gas. So to form 1 mole of ammonia gas, it means we divide the value we have obtained by 2. So we divide negative 93 kilojoules per heat by 2 to get negative 46.5 kilojoules per mole. So this one is kilojoules per mole. So there is an omission of kilojoules here, kilojoules per mole, negative 46.5 kilojoules per mole. So next we proceed and look at Hess law of constant heat of summation. I remember back in high school you were able to look at Hess law of constant heat of summation, whereby you are trying to compare energy change or energy change involved when you move from reactants to products. And you're able to see that amount of energy change involved when reactants are converted to products is the same regardless of the route which is followed by a given chemical process or chemical change. So remember, this Hess law was formulated by a Russian chemist in the year 1840, whereby this law forms a basis of the first law of thermodynamics. So it relates to the law of conservation of energy. And the law of conservation of energy states that energy cannot be created nor destroyed, but it can only be transformed from one form to another. So that is the law of conservation of energy. So that means that in a closed system, the total amount of energy present is always constant. So remember, when you talk about a closed system, no amount of energy is coming in or is being given out to the surrounding. There is no exchange of heat between the system and the surrounding. So Hess law can be used to calculate the standard enthalpy change of a reaction from non-standard enthalpy changes. So first of all, we want to define what is Hess law. How does it state? So Hess law states that the total enthalpy change in a chemical reaction is independent of the route by which the chemical reaction takes place, as long as the initial and final conditions are the same. So the total enthalpy change in a chemical reaction is independent of the route by which the chemical reaction takes place, as long as the initial and final conditions are the same. So that diagram is trying to show or to describe a application of Hess law. So you can see A plus B, those are reactants. Then C is the final product. So you can move from A plus B to F plus G. These are intermediate products before you proceed and form a product. Or you can move from A plus B, which are the reactants, to X. X is what the first intermediate product. Then you proceed to Y plus Z. This is the second intermediate product before you move to the final product, which is C. Or you can move from A plus B, which are the reactants, direct to C. So this one is a direct route, but the upper one is in the first indirect route, and the lower one is the second indirect route. But remember, the amount of energy involved in all the routes is the same as per the Hess law. So this one is the energy cycle diagram. So you have the reactants, then we have the products. So you can move from reactants direct to products, or you can move from reactants, you come to elements, then you move to products. So these are indirect routes. So from elements, you can move directly to products. So this one is direct route. Or you can move from elements, then you come to reactants, then finally you come to products. So this one is indirect route. So this one is called an energy cycle diagram. So enthalpy change from elements to products is equal to the enthalpy change of elements forming reactants, and finally a product, which forms indirect route. So from elements to products, that is direct route, then from elements to reactants, then to products is indirect route. So now remember, enthalpy changes are normally determined under standard conditions, and the standard conditions for determining molar quantities of various reactants is normally 298 Kelvin, or room temperature is 25 degrees Celsius, and 1 atmosphere, which is the same as 1 times 10 to the power 5 pascals, or 760 millimeters mercury. So now, energy changes, the units of enthalpy changes is normally kilojoules per mole. Then we have some important definitions under energy changes. So we are going to consider various definitions under enthalpy changes. So the first one is enthalpy change of formation. What is enthalpy change of formation? This is the enthalpy change that takes place when 1 mole of substance is formed from its elements in their standard state under standard conditions. For example, they are showing formation of ammonia gas, where we combine 1 mole of ammonia plus 2.5 moles of hydrogen gas to form 1 mole of ammonia gas. Then the second type of enthalpy change is enthalpy of combustion. This is the enthalpy change that takes place when 1 mole of a substance is completely burned in oxygen under standard conditions. So the example there, this one is, that one is octane. So when you burn 1 mole of octane in air, you form 8 moles of CO2 plus 9 moles of water. Then part C, we have enthalpy of neutralization. This is the enthalpy change that takes place when 1 mole of water is formed in a neutralization reaction. So for example, when you combine hydrochloric acid and sodium hydroxide, we form sodium chloride plus water. So amount of heat involved in the formation of 1 mole of water is what we call molar enthalpy of neutralization. Then we have enthalpy of atomization. Remember, when we talk about atomization, is the formation of atoms from a given substance. So this is enthalpy change that takes place when 1 mole of gaseous atoms is formed from the element under standard conditions. For example, when you look at chlorine, chlorine normally exists as a gas and as a molecule at room temperature. So 2 atoms of chlorine forms 1 molecule of chlorine gas. So to atomize chlorine molecule, it means we break that chlorine molecule so that we come up with 2 atoms of chlorine gas. So we take a half of chlorine molecule to give us 2 atoms of chlorine gas, as you can see in that equation. So now I want to look at that example. What is the enthalpy change in a kilojoules for the reaction below? So you have been given a very simple equation of the reaction where iron 2 oxide is combining with oxygen gas to form a iron 3 oxide. So that means iron 2 oxide is undergoing oxidation to form iron 3 oxide. Then from this information here, to form 2 moles of iron 2 oxide, we require negative 544 kilojoules of heat. Then to form 2 moles of iron 3 oxide, we require negative 1648 kilojoules of heat. So remember, during formation of substances, there is formation of new bonds. So those processes are exothermic process. Heat must be given out. So now, we are going to look at the energy cycle diagram, which links up those two equations. So this one is the energy cycle diagram. So you can see it. So we have a iron 2 oxide being oxidized in air to form iron 3 oxide. Then here we have a iron metal combining with oxygen to form iron 2 oxide. Then iron here combining with oxygen directly to form iron 3 oxide. So these ones are our reactants. So we can move from elements, these are elements, we can move from elements then to form reactants, then products. Or we can move from elements directly to products. So now from this energy cycle diagram, you will find that here we are forming 2 moles of iron 3 oxide from 4 moles of iron 2 oxide, then here from 4 moles of iron and 3 moles of oxygen gas. So that means for us to move from iron, from elements to form products, to form 2 moles of iron 2 oxide, iron 3 oxide, which will require negative 1648 kilojoules of heat. And for us to form 4 moles of iron 2 oxide, it means we shall double this amount of energy. We multiply negative 544 by 2, as you can see. So let us go back to our equations. For us to form 1 mole of iron 2 oxide from iron, we require negative 544 kilojoules per mole. So that means to form 4 moles of iron 2 oxide, we must multiply negative 544 by 2. Then to form 2 moles of iron 3 oxide, we just require negative 1648 kilojoules of heat. And that's why you can see in that particular diagram, we are multiplying here by 2 because we are forming 4 moles of iron 2 oxide instead of 2 moles. So we have to double this amount of energy. So that means now from this diagram, we are supposed to work out the amount of energy which is required to form 2 moles of iron 3 oxide from iron 2 oxide. So that means to get delta H of the reaction, we shall move from these reactants to elements, then from elements to the final product. So anytime you move against the arrow, it means you reverse that sign. Remember here we shall get negative 544 times 2. So you have put a negative sign outside the bracket, showing that we are reversing this sign. Then plus negative 1648, as you can see from that particular diagram. So when we compute, our final answer is negative 560 kilojoules. So remember you are forming 2 moles, that's why it is just a kilojoules here. But if you were to get in kilojoules per mole, it means we divide this one by 2. So our final answer is negative 560 kilojoules, as you can see from that calculation. So you can use your calculator and compute to see if you can get the sum. So now next we want to move forward and look at experimental information. So we want to see how we can experimentally determine various enthalpy changes. So remember, it is very difficult for you to determine enthalpy change of a given substance or the heat content in a given chemical substance. But you can easily determine it by carrying out an experiment which involves a series of chemical reactions. So it is generally based on knowing the following. 1, we normally use the specific heat capacity of water, which is normally 4.2 joules per gram per Kelvin, or 4.2 kilojoules per kilogram per Kelvin. Then, temperature change of a given mass of water is measured. So the energy change is normally found in that form. So that means M, we normally use mass of solution. Mass of solution can be mass of water or mass of reactants which have been mixed to form a given solution. So now the formula is normally given by heat enthalpy change or heat energy change, which is given by mass of solution times specific heat capacity times temperature change. So remember, this specific heat capacity is normally a constant, which is 4.2. Then temperature change, we normally obtain it by getting the final temperature then from the initial temperature. So final temperature minus initial temperature will give us a temperature change. So then we proceed. This is converted to enthalpy change by dividing the enthalpy change of the number of moles. That one, I think it is straightforward. So look at example 1. This one is a neutralization reaction where we are